Welcome to video 4 of Unearthing Data video presentations with Dr. Brad Heggie. We will begin with step 4, answering the questions with evidence.
I want to highlight again the areas of higher amounts of COVID-19 cases reported. Are those always in the same area, or do they change over time? To answer the second question, let's look at the amount of the number of new COVID-19 cases for each month in 2020, starting with March 2020. You can see as the animation runs that the amount of new COVID-19 cases across the United States increases at first, especially when you compare March to months later in the year. You can see that the maximum amount of cases across the country, the location of those, the maximum, changes over time. As you watch the animation, you can see, for example, if we look in March, that the cases start in the New York City area, but they expand to other parts of the country. So this is evidence here of that the amount of COVID cases across the United States changes over time, where the maximum move to different regions across the United States. So we just looked at the effects of population. We saw that in many cases, but not all cases, there are more COVID-19 cases where there are more people. But let's look at some new data to look beyond the effects of population. We're going to look at a data set that's called incidence rate, which is just the number of COVID cases in a certain location divided by its population. It gives you a percentage of people that have new COVID-19 cases in an area. Here we're showing an animation of this incidence rate from June 2020 to the end of 2020 across the continental United States. Areas that have a high percentage of people reporting new COVID-19 cases are shown in dark blue or yellow, orange, or magenta. When you look at this animation, you see that the patterns of this incidence rate change over time. You can see that the highest incidence rates are not necessarily in areas with high population. So for example, we'll let this run again. You can see that the incidence rate increases across the United States over time. But you can see that there are these yellow and orange areas that appear across the upper Midwest, the Great Plains, and across certain areas in the western United States. As you recall from our population density map, these areas aren't the highest population density areas across the United States. So that means there's something else going on that has nothing to do directly with population density or the total amount of people in an area. So let's look at this incidence rate data further. You may have heard on the news about surges when COVID-19 is discussed. And what they're talking about with surges is an increase of the number of people across the United States who are reporting new COVID-19 cases. These two maps here on the left is the incidence rate on November 20th, 2020. Now, this date's important because it's right before the Thanksgiving holiday in 2020. Right here is the map from January 3rd, 2021, and this is right after the Christmas holidays at the end of 2020. What you can see is that there is an increase in the percentage of population infected with COVID-19 across many areas of the United States when comparing January to November. The population of the United States did not change much between these two dates, so this is not population driven. Let's brainstorm, hypothesize what we might think is causing this increase over this time period. Now, a hint is, as I mentioned, November 20th was right before Thanksgiving. January 3rd was right after Christmas and New Year's Day. If you imagine, or you can hypothesize that people gathered for these holidays and they spread COVID-19 to their family, their friends, whoever they saw during these holiday celebrations. So this is a good hypothesis that we can draw from these data, but of course, these maps don't definitively show that that was the case, where the holidays were the reason for these surges, because it also could just do with the weather got colder and people stayed inside and were next to close family members who picked up COVID-19. There's other explanations here, and to answer that question or to test that hypothesis, we need more data. So let's move on to the connections between COVID-19 and the atmosphere. The key to the connection is to think about how COVID-19 has changed human behavior. If you've lived in the United States or across many areas of the world, you know that COVID-19 drove governments to institute lockdowns and other restrictions on travel and large gatherings of people. And this definitely has had an impact on human behavior and some of the human impacts on the environment. This graph shows an index that tracks passenger vehicle travel across the United States from the beginning of March 2020 onward to the end of February 2021. The source of these data are from the Department of Transportation. You can see by looking at the line plot that there was a sharp decrease in vehicle travel from middle of March up to about June 2020. This period corresponds to the times when the first restrictions on gatherings and businesses occurred in response to the COVID-19 pandemic. As these restrictions were implemented and people chose not to travel because of fear of spreading the COVID-19 virus, you can see that the passenger vehicle travel across the United States dropped significantly, about 40% from the middle of March to the middle of April. So you can imagine that this sharp drop in passenger vehicle travel had a big impact on the environment. But how and what was that impact? Well, let's think about haze and smog. You're probably familiar with haze and smog, especially if you live in an urban area or downwind from an urban area. Haze is just water droplets that are suspended in the air that reduce visibility. Certain particles and gases and particles called aerosols, which are tiny particles that float in the air, when they enter the atmosphere, they encourage the formation of haze. And when some of these gases react, you get what is called smog. Smog can be hazardous to your health, especially if you have respiratory conditions such as asthma. These gases that lead to smog come from both natural sources and human activity. In urban areas, the human activity and the sources from these human activities are especially important. One of the important sources of the gases that form smog is vehicle exhaust, especially for a gas called nitrogen dioxide. If you want to learn more about nitrogen dioxide, I encourage you to look at the teacher slides that are included in the COVID-19 Scientifically Interesting Stories package. Since exhaust from passenger vehicles is one of the main sources of nitrogen dioxide, if you decrease the amount of travel by car in the United States, you'd imagine that this would reduce the concentration of nitrogen dioxide. This is a prediction that we can test, and we're going to test it with a model called the stock or bathtub model. In this model, the stock is a concentration of a gas or a reservoir of a material. The flow are the inputs and outputs of that gas or material. You can think of this model like a bathtub. The water that sits in the bathtub is your reservoir. The flow of water through the faucet that fills the bathtub is the inputs, and the water that drains out of the drain at the bottom is the output. In our example, the stock is the amount of NO2 that we measure in the atmosphere. The inputs are all the emissions of NO2 from natural or human-made sources, and the outputs are all the ways that nitrogen dioxide is removed from the atmosphere. We can use this model in a case study to better understand why we see the decrease or increase in the measured nitrogen dioxide concentration. Here's an example for Los Angeles, California. I circled the measurement from March and April 2020, right about the time that the COVID-19 shutdown occurred in California. Based on the bathtub model, this decrease in NO2 that you can see in the months of March and April is a result of either a decrease in inputs, an increase in outputs of NO2 from the atmosphere, or a combination of both. Here's the same NO2 concentration data, but shown every 2 weeks instead of each month. The red shaded area on the graph shows the dates when restrictions in response to the COVID-19 pandemic started in Los Angeles. You can see that when the restrictions began, and actually a little bit before the restrictions began, NO2 concentrations decreased sharply. An explanation for this decrease based on our bathtub model might be that since the COVID-19 restrictions decreased travel in the Los Angeles area, emissions of NO2 into the atmosphere decreased, and so the amount of NO2 in the atmosphere also decreased. If we explore further, however, there might be another explanation for the drop in NO2 concentration. If we look at a plot of the monthly average precipitation rate in the Los Angeles area in March and April 2020, you can see that there was rainfall over Los Angeles during those 2 months. If you recall from our bathtub model, rainfall was one of the ways that NO2 was removed from the atmosphere. Based on these two graphs alone, we can't tell which process dominated. So this is why we need further evidence to make the argument that the decrease in NO2 was caused by an increase in precipitation, a decrease in the emission of NO2 by vehicles, or both factors. This is why the complex models that NASA scientists create to answer these questions are important. This YouTube video shows how scientists at the NASA Goddard Research Center study effects of COVID-19 shutdowns on NO2 concentrations. These scientists are investigating the same questions we asked today in our data dig.
Video 4 is now finished. Please proceed to Video 5, Step 5 and 6, learning how to create or update your data picture and evaluate and communicate your data picture.